Good afternoon, everyone, and welcome to UH Energy's latest installment in our electric vehicle webinar series. Thank you all so much for joining us on this Friday afternoon, where we'll discuss light duty vehicle greenhouse gases emissions, a transparent dynamic model featuring speaker Jim Crump. Before we begin, we'd like to take a moment to thank our sponsor, Evolve Houston, for their tireless work in increasing the awareness of the benefits of electric vehicles here in the city of Houston. Also, to learn more about our EV webinar series, as well as to find out a little bit more about past presentations, you can visit the website here provided, https://uh.edu/uhenergy/EV webinar series. Also, as a reminder to first time attendees, as well as those who participated in our webinars before, after Mr. Crump concludes his presentation, we'll have a 10 to 15-minute period where we'll have a question and answer session. Feel free to submit your questions as the presentation is ongoing using the chat function, and we'll do our best to answer them. Now, a little bit more about our speaker, Jim Crump. He is a sustainability and energy transition expert. He's got a lot of experience stateside and abroad with energy consulting, having worked for the likes of Exxon, Chemical, and DuPont, as well as Shell. And without further ado, we'll turn it over to Jim and we will get started. All right, Jim, the floor is yours.
Light duty vehicle greenhouse gas emissions, a transparent dynamic model. Let's review a quick outline of today's discussion. First, why study greenhouse gases? Why are they important? We'll answer that. Why build a new model to analyze vehicle greenhouse gas emissions? Does the world really need a new model? Yes, it does. We'll explain. Model structure, accounting. The life cycle framework is a vital and necessary overarching structure for ordering our understanding of emissions and ensuring very consistent vehicle model-to-model analysis. Let's talk about how the model is used. For all listeners, the model is web-enabled. Here is the link. It's also to be made available in a white paper that you'll find on the UH Energy website soon. I invite all listeners to open the model and work with it. You'll find it very interesting, I believe. Then, model-based conclusions and opportunities for further work and information sources. Let me acknowledge Ramanan Krishnamurti, UH Energy faculty sponsor, Preston Satterfield, who rendered very effective service as UH web developer, and Ed Bailey, who gave the prior introduction, communication consultant. Thanks to all. Next slide, please, Ed. Light-duty vehicles, EVs, electric, and ICEVs, gasoline consuming internal combustion. We will examine these two types of vehicles. First, vehicles emit greenhouse gases, intensifying the threat of global warming. Note all, please, that government policies and plans for government expenditure, as well as automaker strategies supporting EV deployment, really are based on the claim that replacing ICEVs by EVs can really cut emissions significantly. True? We'll examine this. EVs were 9% of light-duty vehicle sales in 2021. Manufacturers tell us they intend to increase EV sales remarkably, substantially over the next decade. Now, light-duty vehicles, passenger cars, SUVs, vans, pickup trucks, account for about 58% of vehicle emissions and about 17% of total U.S. greenhouse gas emissions. An important contribution to the overall greenhouse gas emission level from our nation. Now, our model, which we'll get to, indicates the conversion of the light-duty fleet from ICEV to EV would reduce emissions by about 50 to 55%, reducing U.S. emissions by about 9 to 10%. Here we point out, for the moment, exclude heavy trucks. Compressed hydrogen might be needed for their low emission operation. I conclude that EV deployment is useful, but let me emphasize only as a component of a broader strategy to reduce greenhouse gas emissions. Here, let me call out a Energy webinar planned May 5th to examine greenhouse gas remediation in two vitally important sectors, electric generation and industrial facilities, which together account for approximately 50% of all U.S. Greenhouse gas emissions. So yes, vehicles matter, but they can contribute only significantly as a portion of a broader, much broader strategy. Next slide, please, Ed. The value of the new model. The world does not lack for existing models comparing ICEV and EV emissions. Let's just take a glance. A.D. Little, 2016, recognition of lower EV emissions compared to ICEV emissions based on models available at that time, 2015. Reuters, 2020. The insight that manufacturing emissions, yes, are higher for EVs, as we'll see, mainly because of the GHG emission impact of lithium battery sourcing and manufacture. However, lower EV emissions during operation result in what we'll call greenhouse gas break-even, that is the lifetime value where ICEV and EV reach parity. We'll conduct that analysis later using the model. Next, the ICCT regional analysis, US, Europe, and Asia, showed a very important conclusion that the decarbonization of the electricity grid is necessary as the next real frontier for reduction of EV emissions. We'll use the model to examine this claim as well. I mentioned the Argonne National Laboratory GREET model, a vitally important and annually updated database of detailed updated vehicle emission data. Now, why is the present model needed and useful? It offers two very important features that are new. First, complete transparency. The user can see all model components and inputs on a very clear, direct view. That is not true of the earlier models. Inputs are not made clearly available to the user. Second, and vitally, dynamic interaction. The new model, again available on the web, allows the user to not only view inputs, but change them and view the results of input changes on greenhouse gas emissions. My view, a model that you, the user, as well as engineers, scientists, policymakers, that you can see and test is a much more persuasive model, much more useful for understanding the comparison between ICEVs and EVs and for guiding technology and policy discussion of EV deployment. Like any model, this one needs a basis and a focus. Here we're discussing major light-duty categories, standard passenger car. Here for the EV side of the comparison, we'll focus on the Tesla 3, its attributes, its performance, its energy and environmental inputs. For the pickup truck, the EV will be the Ford 150 Lightning. In each case, the Tesla 3 and the Ford 150 Lightning, the comparison will be made to comparable ICEV models based on size and curb weight. Let's move forward. Next slide, please, Ed. We mentioned a moment ago the vitally important life cycle analysis, or LCA. Again, just as every model needs a basis here for EV, car, and pickup, the same for ICEV, we also need a framework. The LCA framework is widely used to discipline our treatment of all emission sources from cradle to grave. Widely used for vehicle emissions and for other environmental analysis. Let's take a look at the form of this framework in the table. Two major phases of the life cycle. First, material sourcing, manufacture, assembly, delivery. Let's take a look. Lithium battery for the electric vehicle only, a significant contribution. Other manufacturing considered for both ICEV and EV. Delivery, again, accounted for both ICV and EV. Turns out to be minor compared to other LCA stages, but still considered. Let's move on then to ownership, operation, and disposal. Tailpipe emissions, well, of course, applied here only for the ICEV. The EV is clean at point of operation, but guess what? To operate an EV, we have to generate electricity, and that generation of electricity across the generation infrastructure creates emissions. So electricity generation considered for the EV. For both the fuel cycle. Now let me pause here a moment. What's meant by fuel cycle? To create motor gasoline, we must produce crude oil, refine it, and transport it to retail sales centers. On the EV side, we have to, in the case of fossil sources, natural gas and coal, we must produce the fuel and again, transport it, in this case, to generation sites. Those greenhouse gas effects from those fuel cycle and supply chain operations cannot be overlooked. Finally, disposal, relatively minor for both ICV and EV, but again, considered in this model structure. So take a look and please take seriously this greenhouse gas life cycle analysis structure. We'll follow it through the rest of this presentation. Next slide, please, Ed. Now, unashamedly some detail here, but I want to show you the full input structure for, on the left-hand side, the ICEV, on the right-hand side, the EV. Now, let me share a rule of life. When one is confronted by this sort of complexity, no doubt about it, there's some complexity here, look for an overarching structure to discipline your thinking and create order to guide the analysis. Here, that source of order is the LCA structure. Let's look on the left. Below vehicle lifetime and distance traveled, both important for later calculations, you will see, please satisfy yourself, that the input structure is ordered in a way that follows the LCA framework. First, manufacture, assembly, and delivery. Then operation and disposal, tailpipe emissions, fuel cycle, and disposal. Now move to the right. EV, the electric vehicle. Again, after vehicle life and distance traveled per year, highlighted in blue, we will follow the LCA structure. First, the manufacture, assembly, and delivery. Here, see the importance of lithium battery manufacture appearing for EV, not for ICEV. And then let's move down to operation and disposal. Here, operation focuses on electricity generation, fuel cycling, and disposal. But let's pause and think a moment about electricity generation. The user will find that very usefully, this model allows the user to alter the generation profile across generation sources listed here, beginning with fossil, natural gas and coal, on through nuclear, hydro, and of course, principal renewable sources, wind and solar, as well as biomass and geothermal. So remember, you can move to the website, open the model, and explore changes in this profile. Now, moving up, once you generate the electricity, guess what? You have to transfer it across transmission and distribution, and you have to load it, charge it to the EV battery. There are important efficiency effects in that entire process. First, after generation, transmission line losses have to be taken into account, indicated here at about 4.9%. Next, when you charge the battery, you lose, estimated here, 13% of total battery charge based on an EPA conformity document for the Tesla 3. And then you run the vehicle at about 3.7 miles per kilowatt hour once charged. All of those effects are important, and it is a regrettable fact of life in the EV world that once you generate the electricity, you have to take into account all of these inefficiencies in getting it into your battery. Now, with that infrastructure, let's now ask, what is the consequence of taking these reference values and calculating greenhouse gas emissions for both ICV and EV for both passenger car and pickup truck? Next slide, please, Ed. Greenhouse gas results for passenger car, graphed at the bottom for the ICEV on the left and the EV on the right. Take a glance first at total tons per year for the ICEV, about 4.9 tons per year. To the right, EV, about 2.3 tons per year. So EV emissions are about 47% of ICEV emissions, with the detail indicated. Now, on the left side, ICEV, tailpipe and fuel cycle dominate. I think that's not a surprise. And we're going to explore the use of the model to really evaluate an important driver of those emission levels, the fuel efficiency. To the right, notice that manufacturer, including lithium battery and other manufacturers, are much greater, yes, greater for the EV than for the ICEV. We'll explore the implication of that difference later when we consider the break-even analysis. On the EV side, electric generation is dominant, and it's, again, the real new frontier for appreciably reducing EV emissions. Now, let me introduce a new form of terminology. You see here CO2e per year. That stands for carbon dioxide equivalent, the same as greenhouse gas. Well, carbon dioxide equivalent, why change terminology? Well, to begin with, let's admit it, it sounds more dignified and scholarly, doesn't it? It does. But it means something. Carbon dioxide equivalent per year, carbon dioxide equivalent really reminds us that the emission level is more than just carbon dioxide, but we must take into account other molecular components of vehicular emissions, notably nitrous oxide and methane, taken into account consistently across the analysis for this model. Capture, please, 4.9 tons per year for car ICEV and 2.3 tons per year car EV. Next slide, please, Ed. Let's take a look at pickup truck. I think it will surprise no one that these emission levels are higher, principally because of substantially greater curb weight of standard pickup trucks compared to passenger cars, as well as aerodynamic profile. To the left, ICEV pickup truck, about 8 tons per year, again noted here as carbon dioxide equivalent. Compare that on the right-hand side, EV, 3.8 tons per year. So a comparison similar in magnitude. EV emissions are about 48% of ICEV emissions. So again, as I noted earlier, replace an ICEV vehicle, car or pickup truck, by an EV, and the reduction in greenhouse gas emissions is in the territory of 50 to 55%. I use a range here, recognizing the margin of error of the model. Now let's move on and take these results for car and pickup truck, and let's draw what I think is the first conclusion in terms of technology and policy from the use of the model. Next slide, please, Ed. Key message. And I want to recommend that Mary Barra and Mr. Ford and all those who are driving electrification of light vehicles, as well as our federal government, please take heed. Electrification alone is a very weak, limited EV policy guidance. And why do I say that? First, reminding ourselves, if you replace an ICEV by an EV of the same vehicle category, so replace an ICEV car by an EV car, or replace an ICEV pickup truck by an EV pickup truck, emissions fall substantially by 50 to 55%. On the other hand, replace an ICEV by an EV of a different vehicle category, and results are widely different. Suppose, for example, you own an ICEV car and replace it by an EV pickup. The greenhouse gas reduction is slight. The numbers shown here, 20 to 25%. Again, using the figures calculated in the previous two charts for passenger car and pickup truck. On the other hand, replace an IV pickup truck by an EV car, a larger reduction, 70 to 75%. The dilemma: the U.S. Energy Information Administration and other sources tell us that today's vehicle fleet is moving in the direction of heavier vehicles, in the direction of pickup truck class categories, which accounted for in excess of 60% of 2021 light vehicle sales. Now, the problem here is that carbon dioxide abatement is vehicle category dependent, and EV adoption leads to much greater greenhouse gas abatement if the new vehicle is a car, not a pickup truck, at least given current technology. My own conclusion: I would be much happier to see our President Joe Biden's smiling face looking at us from the driver's side window of a EV car than an EV pickup truck. The same messaging to leadership of our automotive industry. Now, if you're in the haulage business or you're a rancher, you may need a pickup truck. I understand you can load a whole lot more hay or feed or seed or fertilizer or what have you into a pickup truck than you can into a Tesla 3 car. But are you a rancher? Ask yourself where your heart lies. How important to you is the overall abatement of greenhouse gas emissions? Please consider this car pickup truck difference at the point of purchase of your next vehicle. A personal message, but I would claim based on valid analysis. Ed, please, the next slide. After that first dynamic use of the model, what else can we do with the model? Let's ask some further questions. First, emissions, as we noted, higher in reference to the Reuters study, emissions higher for EVs than ICEVs in manufacturing, lower for EVs in operation. What's the time duration when cumulative emissions reach parity? We're going to analyze that in just a moment using the model. Next, how important is energy efficiency, focusing on the ICV, gasoline usage in miles per gallon? Well, it's very important. It's a very important driver. We'll use the model to analyze that as well. And finally, very important as a model variant will show here, what EV emissions reductions can be gained by further decarbonization of the electric grid. I will mention, but we will not analyze in today's session, the importance of the fuel cycle. Much greater for ICEV, there a much greater emission reduction opportunity than for EVs. But let's take these in turn and use the model to explore these very important technology and policy questions. Next slide, please, Ed. Dynamic use of the model, break-even analysis. Now, break-even time is determined by variation of vehicle lifetime. As we noted earlier, pre-ownership emissions are greater for EVs due to battery manufacture. Battery manufacture, an important fixed greenhouse gas charge for EVs. EV emissions during operations are lower. So what is the lifetime for which cumulative lifetime EV, ICEV emissions are equal, defining break even? Have a look at the graph with me, please. The red line, EV, the blue line, ICEV. As we expect from earlier discussion, at time 0, that's the purchase time when you drive your treasured new EV off the lot. You might say you're responsible for a higher level of greenhouse gas emissions than the ICEV counterpart purchaser. And that's true for a good year and a half, but no longer, because thereafter, the substantially lower year by year operating emissions for the EV take over, leading to lower yearly and lifetime cumulative emissions. So the first dynamic use of the model, break-even GHG analysis. Next chart, please, Ed. Very important, the ICV fuel efficiency. For the car category, a similar analysis applies to pickup truck, but let's focus here in the interest of time on car. Improved efficiency, of course, reduces tailpipe and fuel cycle emissions. You could think of tailpipe emissions and fuel cycle emissions as driven by, subject to the miles per gallon, where that efficiency number is in the denominator. So as it rises, tailpipe and fuel cycle emissions fall. Together, tailpipe and fuel cycle emissions account for more than 90% of total yearly emissions for the ICEV car. Model reference value about 31 miles per gallon. Now let's look at the chart. Recall the number 4.9 metric tons per year at the reference value of 31 miles per gallon for the ICEV car. Now ask yourself, and the model can guide you here, if you progressively improve the fuel efficiency from 31 miles per gallon to a higher value, reducing tailpipe and fuel cycle emissions, how far do you have to go before you reach emission parity with the EV car? Remember, for the EV car, that's 2.3 metric tons per year. The answer is that the fuel efficiency of the ICEV must rise from 31 to about 75 miles per gallon. Well, for passenger car of current standard weight, that doesn't sound easy to me, but who am I to say it's not possible? I think the thermodynamic dilemma in ICEV design and operation is the very large energy loss in the form of hot tailpipe gases. But I think the model is instructive in enabling us to very simply, in a very simple user-defined way, explore this change. Next chart, please, Ed. The next question we raised earlier, decarbonization of the electric grid. To the top, consider major fossil sources and renewable hydropower and nuclear sources. These were listed earlier, you may remember, in the input table format several charts back. Coal, well, about a ton of greenhouse gas per megawatt hour generated. Natural gas, a substantial reduction from coal. And over the course of time, increased use of natural gases performed a very important service in reducing overall greenhouse gases. Natural gas certainly outperforms coal in greenhouse gas terms, but in the long run, that's a low bar. And renewables, hydropower, and nuclear, my hope is sustained use of low emission nuclear facilities are necessary for substantial further decarbonization of the grid. I also want to add, natural gas is a vital component of ERCOT and US generation. Why? Because renewables are intermittent, and natural gas, take a look, for example, at the ERCOT fuel mix website. Natural gas is a necessary, absolutely essential fuel source for compensating in today's world for the intermittency of renewables. What's the solution to the intermittency of renewables? My view, important major advances in grid scale storage. A vital subject, too long to take up in today's discussion, but I want to avoid the apparent claim that the world should run headlong into renewables deployment, accounting for 29 to 30% approximately of ERCOT generation in 2021. Yes, renewable deployment will advance, but the intermittency of renewables is an important ERCOT and US ISO operational issue. Take a look at the source mix with emissions varied by state, and recall that the model allows you, the user, to test greenhouse gas emissions for the electric vehicle based on your choice of generation basis by state. Let's draw some conclusions. At the top, West Virginia, Wyoming. Look at those numbers. What might we conclude? Well, my simple conclusion, high coal drives high emissions regardless of generation levels from other sources. Going further, let's reduce coal illustratively for North Dakota and Colorado. Reduce coal with some offsetting and positive effects of gas, plus renewables and hydro. That takes us down to the US average. Remember, and these calculations are for the Tesla 3, recall the number 2.3 tons of carbon dioxide equivalent per year. Here you see that number. And let's, in my view, say intermediate coal approaching 20%, increased natural gas about 40%, as well as 40% of the total of nuclear plus renewables, US average. Going further, Maryland, South Carolina, higher nuclear, lower coal, still lower coal. So the importance of coal cannot be denied. As we move down this table, the progressive reduction of coal has an undeniable and obviously here measured effect on greenhouse gas emissions. Let's pause with California, our most populous state. Yes, natural gas, but here a total of nuclear plus renewable plus hydro exceeding 50%. Now, California has been called out as a state where this sort of reliance on renewables plus hydro may spell a weakness. Not so in my mind for a number of reasons. To begin with, California, unlike ERCOT, imports 20-25% of its power, wheels power from other sources on a selective and somewhat variable basis. California is a very interesting ISO, meriting further thought on its own. Again, very interesting, but beyond the scope of today's discussion other than that comment. Idaho, Vermont, still further renewable and hydro growth. So undeniably, renewable and hydro need to be increased in their deployment across the US grid. I believe we need to take steps to limit the rate of decommissioning of nuclear facilities, these yes, large traditional fusion efficient facilities if we can. But back to renewables in particular, the pace of reduction of natural gas must be calibrated and managed given its importance in compensating for renewable cyclicality and intermittency. So again, I want to highlight what I will claim to be an important use of model dynamic features, and versatility. I think it's not easy to find another modeling source that will let the user vary these quantities, come to the user's conclusions to validate these results, which I believe to be very important for our public thinking about comparing gasoline-powered ICVs and EVs, for technology guidance, and as well for policy guidance, leading crucially to decisions as to how much money we spend on the deployment of EVs and associated charging infrastructure. So I think the model is paying its freight. It's showing its worth, I will claim. With that, next slide, please, Ed. Now, let's just touch on opportunities for future study. I think there are many. The model could certainly use further work based on, first, refined automotive technology and advances in information sources, no question. A number of other considerations are very worth monitoring. The impact of new battery chemistries and technologies is very important. We've already spoken of the greenhouse gas impact of lithium battery material sourcing and manufacture. Let's keep an eye on competing battery chemistries and other technologies, for example, flow batteries, given the importance of battery-related emissions, as well as energy efficiency and energy density. What do I mean by energy density? Over time, the cost of automotive batteries has fallen, and at the same time, the energy density, the energy capacity per unit volume has increased, allowing progressively for the use of somewhat smaller batteries. And I think we would expect those tendencies those trends to increase. And possibly with some positive disruptive breakpoint as the world finds a readily deployed alternative to lithium ion. Let's keep our eye on diesel trucks. Is compressed hydrogen really required? In today's world, yes, given, and I'll use the term low energy density of today's EV batteries compared to the requirements of the operation of a semi 18-wheeler. But again, new battery technology might disrupt that today's conclusion. Now, finally, the fourth and fifth listed, let's take a closer look at the life cycle analysis framework. And I want to call out here the boundaries. First, the beginning of the cradle to grave framework, sourcing of critical materials for the battery, including mining operations, deserves further work. I also want to call out the fact that mining operations in their environmental impact are not fully stated by greenhouse gas evolution, given the importance of airborne particulates, which have been implicated in very serious respiratory ailments. At the other end of the LCA boundary, let's think about what happens to a vehicle at end of life. Battery recycling today is disfavored compared to landfill disposal, not just on greenhouse gas or environmental grounds, but also cost and energy. Are transformative advances in recycling likely? I doubt it for several reasons. In my view, that operation is heavily manual. And what is more, I think it is difficult to stimulate enthusiastic investment in a battery technology that investors realize might change. Well, that is my summary of why vehicular greenhouse gas levels matter and why the world needs, and I hope that these readers can value, a new model which shows the reader all inputs and allows you, the reader, to vary those inputs to explore user-defined scenarios. Ed, let's pause there Again, thanking our audience. Let's move on to the final chart, which moves us back to the introduction. Let me just mention one more chart, please, Ed. Yes. For all users, selected sources for model development are available. I will not review them here. They're available in a white paper that Ed is going to help us get up onto the UHMDT website soon. All of these sources and others will be listed. And let's go on to the very last chart, Ed, which takes us back to the outline. Now, for all readers, again, all listeners, thank you for participating. As a reminder, here's where we've been. Ed, let's open it up for questions. Well, I'll go ahead and dive in here, and I'm going to try to read from the chat box here. Yes, the EVA LCA. Let me point out that, in my mind, the problem of short-term battery life has been exaggerated. And I want readers to reflect on the fact that Tesla, go to their website, now offers a warranty for these light vehicle class of batteries, a 120,000 mile warranty, much longer than I think that the public has expected. These numbers were taken into account by the Department of Energy Argonne National Laboratory, and so it is anticipated, certainly as technology advances, based on the DOE Argonne National Laboratory analysis, that battery tax changes are not a serious factor in the lithium battery used by an EV. Even if they were, double that number that you see earlier, and I don't think you would change substantially the conclusions as to the overall greenhouse gas evolution. But good question. Let's move on. Can you move on to the next question, Ed? Help me see it, please. Let's see. Can I comment on the effect? Let's see. Can I comment on the effect of the model on autonomous vehicles? Would there be a different impact on EVs and ICEVs? I doubt it, because it is difficult for me to understand how autonomous vehicle deployment would make a telling difference between the operation of an autonomous system and driver instincts. But what I would say is, I think that that's my view, but good question. And let me go on to say, the move to autonomous vehicles is very important, because I think that it will be the pathway for the conversion of limited range delivery vans and other forms of commercial and municipal owned vehicles in the EV world. So I think it is very important as an EV enabling technology. Next question, please, Ed. Let's see. Looking on, let me try to read it. And don't ICVs become less efficient over time, so that the lifetime cumulative graph should be concave rather than straight line? Well, I think that the same could be said for EVs, and I think that a stronger analysis might restructure both lines in detail. In my mind, the important thing is the dramatic difference between short range and long range operation. I think that an important difference is that for the ICEV, parts can be replaced readily compared to the EV. An ICV that's been on the road for 15 years might well have a new transmission. It might well have a new engine. And those effects are taken into account by the Argonne National Laboratory estimates used here. That's much more difficult for the EV. And I would also say, yes, the structure of those two lines in the break-even analysis could deserve further analysis. My personal doubt is that the broader, the higher level change or the higher level conclusion would not change a great deal. But it's an interesting question and useful analysis. Thank you. Next question, please, Ed. I'll go on and read. Do I have data on SUVs and hybrids? SUVs are increasingly classed close to pickup trucks, and therefore we simplify the analysis by comparing pickup trucks and cars as an overall comparison of truck weight vehicles versus car weight vehicles, where trucks, the overall truck class would include pickup trucks, minivans, and SUVs, overwhelmingly dominated by pickup trucks. Now, let me comment on hybrids and explain why I've not focused on hybrids. And I will also point out that UH Energy, there is research within University of Houston considering the long-range costs of hybrids versus EVs or so-called BEVs. The issue with hybrids, again, a view, a claim, subject to debate, is that in the very long run, hybrids will be difficult to manufacture, even with mass deployment at steadily declining cost of manufacture, because of, face it, the inherent complexity. Stop and think about the fact that a hybrid requires two separate drivetrains and a guidance mechanism for coordinating the two. Straight BEVs and ICVs, only one drivetrain. I think that we're seeing cost trends in manufacture and cost projections that tell us that fundamental difference in manufacturing complexity will be telling in the long run. But thank you for the question. Another question, Ed? Let me reach down and grab one. I'm a little ahead of you here. Mention the difference between efficiency depending on energy source. What about energy produced from hydrogen? It's not hard. I mean, it's not hard in today's world conceptually to produce hydrogen from so-called green means. That is, from electrolysis operations that are based on wind or solar operations. However, that technology is emergent, rather distant. And after all, you have to pay for the conversion operations for hydrogen. Also, I don't conceive in my mind an advantage of hydrogen over battery technology for cars, particularly given the expected ongoing advancement of low emission sources for the electricity grid. It appears to me that there is a very clear pathway before us for progressive reduction in electricity infrastructure, greenhouse gas emissions, and therefore emissions from electric vehicles. Again, I want to add the caution that natural gas will be continued in use for some time, I think, because of the cycling effect of renewables. But I think that hydrogen has a necessary place for diesel-powered transports. Why? Look, when you compress hydrogen, you reach a energy density which is about 2.5 times that of motor gasoline. That's the sort of energy density you need to power a semi 18-wheeler. Today's batteries cannot match. You can't start and accelerate an 18-wheeler today effectively with a reasonable EV battery weight. You need hydrogen. So, as I remarked earlier, I think that given today's technology, hydrogen is necessary for that important contribution to vehicular emissions. We said earlier that light vehicles account for about 17% of all greenhouse gas emissions. Diesel-powered transport, something like 7 or 8%. So the deployment of hydrogen for diesel transport is another useful contribution in the long run to greenhouse gas abatement. Let's go on to the next question, please, Ed. Let's see. I see a long one here, Ed. Each gallon a consumer uses gasoline, 20 pounds of CO2 or nearly 90% of the emissions problem. Let's see. Each gallon of I think motor gasoline here that a consumer uses generates 20 pounds of carbon dioxide or nearly 90% of emissions problem. What are your thoughts on consumers voluntarily offsetting their own Scope 3 tailpipe emissions at the additional cost, at least at the inner solution, a behavioral nudge to eventually adopting an EV? Well, by voluntarily offsetting their own Scope 3 emissions, I guess, what might that mean? Drive less? That's my solution. But I think that the listener, the questioner, points out a very interesting problem. First, I agree with the overall emissions level per gallon of gasoline. That number in a congressional research study used for this study turns out to be about 9 kilograms of greenhouse gas emission per gallon of motor gasoline. Yes, about 20 pounds. And corresponding number for those interested, about between 10 and 11 kilograms, so between 20 and 25 pounds per gallon of diesel. But I accept the point that EV adoption should be in our minds as we think as responsible citizens toward a better world in which we abate overall greenhouse gas emissions and act on the global risk of climate change. Thank you for the question. Next question, please, Ed. Let's see. I'm looking here. Let's see. Can I please say more about any initial findings regarding reduction in the ICV fuel cycle? Impact of most synthetic fuels are produced with a significant lower CI scope. True. If you substitute, and I'll take, let's take each one. Ethanol as a basis for fuel, or synthetic diesel, or other forms. Yes, these technologies can reduce greenhouse emissions, but I have two cautions. First of all, one of the advantages of electric vehicles is not only do they reduce overall greenhouse gas emissions, but tellingly, they reduce the urban concentration of vehicular emissions, which, because of, in particular, ozone and particulate emissions, are responsible for serious and sometimes life-threatening respiratory ailments. There's nothing that I see in the synthetic world that reduces that, in my mind, very important pattern or pollution footprint from these fuels. What is more, it seems to me that from what I've seen of costs, and add to that the already recognized and in progress nationwide movement toward reduction in grid emissions, the more dominant vehicular effect will be, one, from the transition from ICVs to EVs, two, the progressive reduction in grid scale emissions from electricity infrastructure? Thank you for the question. Let's go on, Ed. Who's next? I'm going to go on down and say, let me grab one that I think is very important. I see one on lithium. Is there enough lithium in the world and cost of lithium? Let me address that one, Ed. A very critical question that was not addressed in this webinar, but I think would make it a very interesting follow-up, is the sourcing not only of lithium, but let's just say lithium-ion battery critical materials, lithium and cobalt, for example. Well, lithium, Chilean, Bolivian, Australian sources, for example, yes, are limited. And I've seen a published estimate that would say, given present and 2022 through 2026 or 7 lithium consumption, new sources will be needed. And we rely on distant parts of the world for lithium, a critical and a very important question. That is why lithium mining, prospecting, and technology development are alive and well elsewhere in the world, including the United States. But let me focus on the other now critical material that I just called out, and we'll mention only two here, lithium and then cobalt mineral. The world relies almost entirely on the Republic of Congo for cobalt supply. I think that is an even more focused and perhaps more dramatic case of reliance on a foreign source. And it also calls to mind that both for mining of lithium and for cobalt, I'll repeat the point that mining is a process that does generate greenhouse gas emissions, but also other forms of pollution. So I think that, yes, the questioner is right. Lithium, but let me add cobalt mineral, are critical materials whose sourcing operations should, yes, concern us. Thank you for the question. Let's move on, Ed. Next question. Well, thank you to all. Ed, I think we've come to the end of the hour. I wasn't watching the time, but thank you all. And let me recommend that all go to the website to see the white paper here that will repeat these conclusions as well as extensive references. Thank you all for your time today.